So as I said, I am Varsha and I'm a postdoctoral fellow at the Indian Institute of Science. Today I'll be describing the highlights of one of our works titled Find Thy Neighbourhood, Privacy Preserving Local Clustering. This was joint work done with my collaborators Pranab, Nishad, Arpita, Bhavish, and yeah. So I'll begin by describing what exactly do we mean by local clustering and the need for privacy that arises when computing the same. I'll briefly describe the contributions of our work and maybe give a high-level overview of the secure solution that we have for local clustering and maybe give some benchmark results. So as you all must already know, there are many real-world applications where there's a need to store data in the form of a graph. For example, the entities in the system could be modeled as nodes, and the interaction between the entities can be captured via edges. And a few common examples are social networks, contact networks, and several others. Once you have the system represented as a graph, there are several algorithms that are designed to understand the characteristics of the underlying graph and thereby comment on the properties of the system. And one such commonly used technique is that of clustering, where the objective is to identify nodes that are similar to each other. But most of the works that's there in the literature focus on performing global clustering, where the objective is to categorize each node in the graph to belong to some particular cluster. But what we are interested in, and which is necessary for some application scenarios, is to ideally identify a local cluster or perform local clustering. That is, you are given a seed node, and rather than focusing on categorizing all the nodes in the graph, you're just interested in identifying nodes that are similar to the given seed node, right? For example, let's consider a simple application scenario. Let's say you have access to financial transaction network, wherein each node could represent a bank account, and the interaction between the nodes would represent the financial transaction that could happen across the accounts. Given this financial transaction network and access to the information that some particular node is actually a fraudulent node, you may be interested in identifying other potentially fraudulent nodes by looking at a local cluster around the given seed node, right? But as you can see, in order to do this, you would require access to the entire global transaction network, which is usually split across banks, wherein each bank would only have its a subgraph of the entire graph that represents the underlying transaction network. And in fact, banks could regard their view of the graph to be private because financial transaction information is definitely sensitive. But collectively, these banks could be interested in identifying fraudulent nodes, which could be spread across multiple banks. So this is one such example where we could be interested in performing local clustering. So the objective of the current work was to design a privacy-preserving variant of local clustering algorithm. And the assumption is that the global network, or the global graph that represents the underlying system, is distributedly held in such a way that there are multiple data owners that hold the entire graph, and each data owner only sees a partial view of the network. And the objective is to identify a cluster or a local cluster around a given seed node in such a way that individual privacy, that is each data owner's privacy, is not compromised. So as you can see, this can be clearly modeled as an instance of secure multi-party computation, or MPC. I'm sure most of you must already be aware, but since this is the first talk with MPC here, I'll just quickly go over the same. So secure multi-party computation, or MPC, essentially allows a set of parties to jointly compute some function on their private data in such a way that the following two properties are guaranteed. The first is that of correctness, which ensures that whatever is the MPC protocol that you design, the computations that you perform and the output that is generated at the end of the computation is in fact the desired function output. That's what correctness guarantees. And the second property is that of privacy, which means that during the run of the computation, or whatever is the messages exchanged or the computations performed, the computing parties learn nothing other than the final output. This is what is guaranteed through privacy. And in fact, MPC protocols can be designed to guarantee these properties of correctness and privacy, even when some of the parties, computing parties, can misbehave and maybe deviate from the computation that they are supposed to do. Specifically, in our work, we make the following design choices. The first thing that we do is we assume to operate in a secure outsource setting. What do I mean by this? We assume that there are computationally powerful servers that can be hired to enact the role of parties in an MPC protocol. So you have these servers that are performing the computations on behalf of you. And we consider access to 3 such parties. So we are operating in the 3-party setting. And we assume that at most one of the parties could deviate from the protocol, or at most one party could be malicious. So this is what I mean by the honest majority setting. That is, we assume that there's honest majority among the parties, but at most one could deviate. Further, keeping efficiency in mind, we design protocols in a framework known as GraphSC, which is a generic framework that allows you to design secure protocols, specifically when dealing with graph algorithms. So they give you an efficient way to realize graph algorithms securely. So we also ensure to design protocols using the same. And the contributions can be stated as follows. So firstly, we identify the state-of-the-art algorithm that in clear text, which is capable of identifying a local cluster around a given seed node. And as I said earlier, it's about identifying nodes that are similar to each other. So when you're performing local clustering, you need access to a metric or a measure that is capable of quantifying how similar given 2 nodes are. So as in we rely on this metric known as heat kernel page rank, which is known to give the best quality cluster. So we also identify the state-of-the-art algorithm in clear text that is capable of computing the heat kernel page rank value, or HKPR value in short. And having identified the clear text algorithms for these, we design a secure variant of these algorithms in the 3-party setting. We rely on the existing framework, MPC framework known as Swift, which also operates in the 3-party setting. And as I said earlier, we ensure to, when we are designing the protocols using the framework of Swift, we ensure that they are compliant with the GraphSC framework, which allows us to efficiently realize graph algorithms. So at a high level, this is what we do. When we operate using the GraphSC framework, the solution entails 3 steps. First, we have the clear text algorithm, and in order to design them in GraphSC, we require to translate the same into a message passing algorithm. So we first do that, and once we have obtained the message passing algorithm, we design data oblivious equivalents of the algorithm. So what do I mean by data oblivious algorithm? Usually algorithms that are designed in clear text don't really care about privacy. So we translate the steps of the algorithm in such a way that the sequence of steps that is carried out in the algorithm remain invariant to the input that's given. So you want to ensure that the same set of sequence of steps are followed and the memory access pattern remains the same, independent of what the input is. So we design a data oblivious algorithm for the clear text algorithms that we have. And this essentially boils down to defining the 2 primitives known as scatter and gather that are the key primitives that define the GraphSC framework. So we do that, and once we have the data oblivious algorithm, it is pretty straightforward to get the underlying MPC protocol. With respect to local clustering, our contributions are as follows. If we were to naively translate the clear text algorithm into its secure variant, we would have an algorithm which would have complexity of order V times V plus E. But we observe that certain things can be done cleverly, and our approach ensures that the overall computations can be reduced to just order V plus E. And this can further be improved via the GraphSC framework to achieve up to log of V plus E improvement. With respect to heat kernel page rank, although asymptotically we don't improve the underlying algorithm, we observe that there are some redundant computations which can be clubbed, and overall we reduce the overall computation cost of heat kernel page rank. And by choice of the clear text algorithm, we are in fact able to give secure variants for several other measures apart from heat kernel PageRank. And in the process of operating on the existing framework of MPC, which is the three-party framework of Swift, we enhanced the framework by designing primitives that were required for local clustering, which were essentially not present previously. So we designed some of the missing primitives, and we also adapt an existing shuffle protocol to work with the framework of Swift to ensure that we are able to do local clustering as we desired. And we also benchmark our protocols to showcase the practicality of the same. At a high level, okay, I am not sure that I'll be able to go into the details of the algorithm. So at a high level, what we observe is the following. The local clustering algorithm essentially computes the heat kernel PageRank values, and based on the heat kernel PageRank values, it iteratively identifies clusters by including one node each time, and the objective is to identify a cluster which has Cheeger value to be the minimum. So we have another measure known as Cheeger ratio, which essentially quantifies the quality of your cluster. So you want to be able to identify that cluster which has the lowest Cheeger value. And our contributions here are as follows. In the naive approach, what is done is each time you're adding a new node to the cluster, computations are performed as in repetitively. So what we observe is you can in fact compute the Cheeger ratio of your next cluster based on the computations that you have already performed. So we leverage the fact that the clustering algorithm is actually iterative, and we define a new notion known as greater count, and which allows us to sort of do additional bookkeeping, which is what allows us to reduce the complexity from order V times V plus E to order V plus E, which can further be reduced to log of V plus E through GraphSE. We also showcase that our protocols can be run efficiently. In the multiprocessor setting of GraphSE, we observe that it takes about a few minutes to compute the local cluster. So in general, the paradigm that we followed is as follows. We identified the state-of-the-art algorithms which were not data oblivious, and we basically designed data oblivious algorithms for the same and translated them into secure variants using the existing MPC framework of Swift, and appended the primitives that were required to Swift. Yeah. For further details regarding the benchmarks and any other questions, I would refer you to the full version of the paper.
So let's quickly thank our speaker. And first question online is, could you please elaborate on what went in while making the framework of Swift compliant with the GraphSE framework?
So Swift as a framework was designed for privacy-preserving machine learning specifically. So it didn't really have a shuffle protocol. When operating on GraphSE, one of the primitives that is required is, given a list, you should be able to shuffle the entities in that list. So that was not present in Swift. So we essentially adapted one of the existing shuffle protocols over the secret sharing semantics of Swift.
Are there any questions in the room? Which questions do you have in the room? Then I'll just follow up with another question from online. As adding new nodes is repetitively, how is the computational cost in practice?
So what we've done is just micro benchmarks, but because we are operating in the pre-processing paradigm, which is essentially coming from Swift, the online cost is, even if you have, let's say about, if your graph is in the order of 10, like 1 million node and edges sized graph, then it takes about a couple of minutes, I suppose, to perform local clustering. So I think that is good enough time to identify, let's say, the infection spread or spread of rumors. So I think that's good enough.
Okay, thank you. Is there any more in the room? If there are no further questions, let's thank our speaker.
Thank you.